That long, really, in the grand scheme of things.
And you're on. So this is
excellent. Right.
Fantastic.
There we go. Cool. Okay, we're all being incredibly silent because we're scared of the live streaming. Excellent. Sounds like a good start. Okay, so I'm just going to pretend that's not happening. All right, so remind me who's who. What are your names?
I'm Kamiko.
Kamiko?
Joyce.
Joyce. Right. Okay, so we're doing A2 chemistry. We've got an hour and a half. It's 5 o'clock now, so we're aiming for about 6:30. Cool. How many questions are in this paper? Let's have a look. 7, 9. Right, 9. So cool. 10 minutes for a question. I'll do. All right. So, how should we go about doing this? Okay, since we're in person, so you guys have had a go at this paper already. So why don't we start by just trying to have a look at some of the questions that you guys found the hardest, and then if we run out of those, we can just kind of run through them in order. But I mean, it makes the most sense to go for whatever you would like to talk about first of all. That seems like a good idea. So
we just didn't get understand on the question 3, part 2.
Question
3.
3.
Part 2.
Oh, I'm losing 3A part 2. E5 cell. Oh, right. Okay. So we're on electrochemical cells. Nice. All right. So.
I mean, like, we know how to do it, but it doesn't make sense, the answer. I mean, so.
Okay. So which one of you's got the mark scheme?
That one's answer.
Right. Let's have a look at this.
The blue one. But.
Okay, so you've got the values from the data booklet.
Yeah.
Where's the mark scheme? Is it attached to the back of this, or? God, can you like unstaple it? And, yeah, there we go. Cheers. Thank you. Right. So what have they got in the mark scheme of this that doesn't make sense? Let's have a look. That's question 4. This is just in a really weird order. What's going on here? Okay, question 3, A part 2. Okay, so you have multiplied one of them by 2 for no apparent reason, or according to the mark scheme at least. So why have we multiplied something by 2? And
no,
not.
I did multiply 2, but the answer said we don't have to do it. But
yeah,
but I didn't get why don't have to do.
Why don't we multiply it by 2? Yeah. So what I'm guessing is, we've got 2 standard reactions that we're putting back to back here, right? We've got the iron equation, and we've got the chlorine equation. Both of them have in fact been doubled, as far as I can tell. Haven't they? Yeah, kind of. So, have you got your data booklet?
Yes.
What I was going to say, because the most important thing is what values is your actual data booklet giving you them for? Hold on. Yeah. Oh, yes. Okay. Okay. So, right. The essence of this is, yeah, I remember this one now. So basically, when you are calculating electrochemical cell potentials, you don't work with the actual ratio of the equations for the cell potentials, right? And essentially, this makes more sense if you think about it in an actual physical context, right? Because these are the potentials that are reached by the electrode of a given cell, right? What we're looking at here is the molar ratio if you actually react them. But in practice, what we're doing is we've got one cell that looks like that with a pool of, the iron ions, and we've got another entirely separate cell with a pool of chlorine ions, right? So what these numbers are, these are the potential of a cell which is a pool of those things, right? So the ratio at which they're reacting doesn't change the fact that at the end of the day, you still have a piece of metal sitting in the water being at that potential. So what the ratio tells you is how fast will you use one up relative to the other, right? So you'll need twice as much iron to chlorine in this case, like twice as many moles of iron ions compared to chlorine to go through the whole reaction. So you'll use the iron up faster, but at the end of the day, you've still just got a pool of, you've got your electrode sitting in a solution of iron ions. And if I keep saying iron ions, I'm eventually going to mess up. But so does that kind of make sense, right? So it's essentially that cell, that beaker of solution with an electrode in it, has a certain potential, right? A certain electrical potential. And it's the difference between them that gives you your driving force. The molar ratio is separate to that. The molar ratio is about how fast are you using those up. So in a way, the molar ratio will determine, in a lot of ways, your current and stuff. It determines how fast you're using one up relative to the other, but not the actual voltage itself. The potential is just determined by what reaction is going on, not how much of it is happening. All right. So yeah, that is a bit of an odd one, because literally everything else in chemistry, it's always about how many multipliers and ratios and all of that. This is the one time where it makes absolutely no difference, and it's a bit weird. But as I say, I think it makes a lot more sense when you think about it as a sort of actually I've got these two isolated beakers that are just kind of doing their own thing, because essentially the idea is that actually that iron beaker, right, it has no idea what is attached to the other end. All it's got is a wire coming out of it that it's pumping electrons into or taking electrons out of. So it has no idea what the molar ratio should be, because that's actually, if you physically stick them in and react them, we're not doing that. We're just kind of attaching them in some pools and throwing electrons around. Yeah. All right. So hopefully that was handy. Okay. Do you want to talk through the rest of this question while we're at it? Just kind of have a look, or so yeah, cell potential. So that's your standard hydrogen electrode. You were fairly happy with that. So what you've got sort of platinum electrode and all that kind of stuff. Yeah. All right. So then we had the E cell that we've just talked about. What color change would you see? Predict the effect. Okay, yeah. So these are essentially, so the first one is essentially just a learn it one, decreasing the concentration of chlorine minus. So what did you say about that?
So maybe like changing voltage, like decrease or increase. I said increase of voltage.
Yeah. Okay, cool. Yeah, so the general idea is, so this is essentially where these two concepts come into, what would you call it? Kind of come into conflict a little bit, which is why it's worth talking about, right? Because this actually directly goes against what we've just been talking about. So the potential of a cell is not fixed at these. So these numbers here, right? These are actually very, very specific. So these are specific to standardized conditions. So these voltage numbers are for are for like essentially 1 molar concentration of anything and everything at standard conditions. So once you start changing the concentration, so in this case, making your chlorine more concentrated, you're going to make that cell do more of whatever it's doing. And it's just worth kind of separating that version of concentration changing things from the kind of molar ratio stuff that we were talking about up there, right? So this in here, what we're doing is we're changing one of those cells. So again, it has no effect on the other cell. We're just talking about that one cell. And so essentially it's just going to do more of whatever it's already doing. If that makes sense. So in this case, as we decrease the Cl minus, we've got our, what's his face's law? I don't remember. But so because we're losing stuff on the right-hand side, we're going to do more of the forward reaction. Yeah. And given that the forward reaction is making it positive, it's going to get more positive. If we raised the concentration of Cl minus, it would get more negative because it would go slower. Yeah. Or less positive, more negative, it's the same difference. So yeah, I think the concepts of electrochemical cells are probably one of the harder conceptual parts for A2 chemistry. It's one of the ones that people always struggle the most with. So yeah, don't worry too much about struggling with it. It'll come with time. But yeah, they are fairly tricky. So you know. All right, and then we've got fuel cells. So fuel cells are essentially an exercise in learning a lot of things. And I don't know if people still think this. Once upon a time, people thought they were the future of cars. I don't think they do anymore, but you know, exam syllabi take a while to catch up, so they still want you to know about them. So yeah, there is very little understanding to be done there beyond the understanding that we've just talked about. As long as you understand the actual, you know, the concentrations and stuff, how that works with electrochemical cells, that's the only understanding bits that they ask you to apply. So the only kind of tricky parts that they tend to ask about these outside of so this one, it's just all, you know, things that you need to know, essentially, right? It's not fun, but, you know, that's just life. The only kind of thinking type questions that they tend to ask about these are kind of talking about if I raise or lower the concentration of oxygen or something like that, what's going to happen? And that's what we were just talking about, where it's going to change the voltage of the cell. All right, so I think that's probably okay for that question. So where would you like to move on to next? Pick a question. Oh yes, sorry, my apologies. I've just stolen it from you. Right, so basically, I mean, I would hope you'd probably kind of remember if there were. Basically, I'm looking for any questions that you had a lot of trouble with, essentially. You know, things like this where it's going to take a fair amount of time because we want to focus on those first. If you don't have any of those that you want to talk about, then we can just kind of try and work our way through the whole paper in a bit less detail, essentially. Should we do that? Yeah. All right. Basically, I just want to make sure that we don't not have enough time for the ones that we really need to focus on like that, because that took a little while longer. All right, so let's go through from question 1 then, if I can find it. There we go. So this is our enthalpy change of solution / ionization. I'm unscrewing the pen, that's a little worrying. We'll just hope for the best. Okay, so what should we say about, where should we go from this? How were you guys on this question? You know, how did you guys find it?
answer ionic bonds are great, but it's only
Right. Okay. So basically, I'm doing kind of a miniature version of the paper thing. So when we start, question 1, question 2, basically, I'm just kind of asking, how, were you guys super comfortable with this, or were you struggling a little bit? That's all I'm kind of looking for. So yeah, we'll just kind of talk through it briefly. So bond breaking, bond making, what happens in the solid ionic lattice when an ionic compound dissolves. So 2 marks. So this is general exam technique that I'm sure you guys are comfortable with by this point, but it's always worth reiterating. The number of marks is key to, how many points am I trying to make, right? So in this case, we're making 2, and that's easier so bond breaking, bond making.
Yeah.
So essentially what we're looking for here is what bonds break, and then what bonds do we make? And those are our 2 points, right? So you've just said, obviously, ionic bonds are what we're breaking, right? We had an ionic lattice, we don't anymore, so that's what we're breaking. That part's nice and easy. What are we making here when we dissolve something in water? Do we have any ideas? Yes, hydrogen bonds, okay? So water has hydrogen atoms bonded to a strongly electronegative atom, i.e. oxygen in this case. Water makes hydrogen bonds. That's like basically the most important thing about water. It makes hydrogen bonds, and lots of them, and very strong ones. So yes, we're breaking ionic bonds, and then each ion is forming actually quite a lot of hydrogen bonds with water molecules. And what you actually end up getting is each ion will be surrounded by a whole cluster of water molecules that are pointing one way or the other depending on its charge, and hydrogen bonded to it. So yeah, those are your 2 points. What is meant by the term enthalpy change of solution? That's kind of fairly self-explanatory, and that's a definition. I would argue that the name itself is kind of fairly, it's the enthalpy change when you make a solution. But obviously they're looking for something ever so slightly less. What do you call it? This mark scheme is in complete disarray. It's quite bizarre. Did they have anything? Oh, okay, yes. So they're looking for the whole sort of 1 mole dissolves in water type of definition. But yeah, so we won't spend. Yeah, I'll try not to spend too much time on things where it's just kind of you need to know it, because as I said, they're not fun, but at the same time, there's not really a lot to say about them. Okay, use the following data, calculate the standard enthalpy change of hydration for chloride ions and make an energy cycle. Okay, so hydration magnesium. Yeah, okay, so this one, you're looking at essentially your cycle. So you're breaking your lattice apart, and then you're hydrating both the magnesium and the 2 chloride ions. So you're looking for the difference, and then you're dividing it by 2 because there were 2 of them. That's quite nice as far as enthalpy cycles go. Just a brief thing to mention, actually, since I haven't really spoken to you guys before, and it's always worth talking about. Enthalpy, what is it? There we go. That always gets people. You deal with it a lot. It's very rarely talked about what it is, right? Essentially, it's a lot like kind of energy and stuff like that, except it's a kind of more useful thing for chemistry. It works at constant pressure. That's what's important about enthalpy. Yeah, it's essentially energy in chemical bonds is the best way to think about it, because that's the way that you usually come across it. There is more to it than that. There's more to everything, but always that's just kind of life. But the best way to think about it is essentially energy that's specific to chemical bonds, because for chemistry, that's what you see of it. But it's worth kind of having some idea in your head so that when I ask you, you don't just suddenly both look at me really afraid like you did just then, because, you know, you never really want to have that reaction to a question. Enthalpy change of hydration for sodium plus is this. Why is sodium less exothermic than the magnesium 2+ ion? So in this case, what was your suggestion?
I said MC's got higher charge
Yep.
than sodium.
And what's that going to mean?
They got more attractions.
Yeah, so it forms stronger hydrogen bonds, essentially, right? It's like, you know, hydrogen bonds are essentially a very much weaker version of ionic bonds, right? And so essentially, the stronger the charge, the stronger the bonds. And in chemistry, as a general rule, the stronger your bonds, the more energy you're putting in or getting out when you break or form them. Yeah, so stronger bonds means more energy, and stronger charge means stronger bonds. That's a kind of those are good rules of thumb to have at hand for kind of questions like this, because this is not the sort of thing that you want to necessarily try and learn off by heart. That, you know, specific things about the enthalpy change of hydration, like that's oddly specific. This is about sort of generally applying your rules of thumb with kind of charge and energy and bonds and stuff. So yeah, rules of thumb are better to learn than kind of very specific things, because it's less to learn for more uses, right? It's saving you time, and especially in this kind of, you know, trying to spend only half your days on stuff, it's worth doing. Okay, how does the solubility of the group 2 sulfates vary down the group? Fair enough. That's an odd one, but there we go. So, how does it? Talk to me.
It's going to be decreased because energy. Yeah. So solubility decreases because energy is also decreased. It doesn't really make sense.
Okay, so this is a 4-mark question.
Yeah.
So I would really, really like to find mark scheme for this, but I can't because this is all really weirdly printed. Page 2, A, B, C.
1C.
This is 1C, not 2C. That would be why I can't find it. Okay, so basically, again, as a kind of rule, 3 is kind of iffy. Once you get to 4, essentially what you are looking at is a bullet point question. They never say write in bullet points, but it's worth realizing that actually, so I mean, if you have a look at the mark scheme, right? The mark scheme for this is 4 bullet points. That's quite harsh in this case. It's a 4-mark question and they have 4 bullet points. So you need to get exactly those 4 and there's no leeway on that. As you get more marks, generally speaking, it'll be, you know, you need 5 of these 7 bullet points or something like that, right? In chemistry, for your syllabus, there are none of these sort of quality of written communication things, right? They are never testing you on your grammar and your ability to write beautiful sentences. So my advice personally would be don't, right? It is quicker and it is also more clear to you what, you know, how many marking points have I tried to hit, essentially. It's a little bit of a cynical way of thinking about it, right? You know, aiming for marking points rather than explaining things, but at the end of the day, it's an exam. Bullet points are faster, they're easier to do, and it makes it clearer to you, you know, have I made 4 points? If I have, good. If I haven't, I need to find another one, right? The mark schemes are always bullet pointed. And so it also makes it easier to A, mark your own work when you're in this situation, and B, it makes life easier for the examiner. And you should never underestimate the power of doing that. A little bit of goodwill will go a long way. So yeah, that's something that's worth talking about. So essentially, I mean, you can do it for everything, but sort of 3 marks varies, 4 marks and above,
Yeah.
write the number of aim for the number of bullet points. Sometimes aim for +1, just to kind of give yourself that buffer of, you know, at least one of these can be not on the mark scheme. But yeah, so in this case, we're saying, okay, solubility decreases because our lattice energy and hydration enthalpy are decreasing. And basically it's because your bonding is getting weaker. As your group 2 ions get bigger, they do weaker bonding, and so less is going on, essentially. That's your general idea. Yeah. So I guess I've talked more about exam technique there than I have about the actual question, but if you were okay with the question, then I think we can move on. I think that's actually, to be honest, the more useful thing to take away from this, because it applies to a lot of things, and it applies to basically all of the other science-based subjects as well. You know, chemistry, biology. I think biology, sometimes they have some longer QWC ones, but anything that doesn't explicitly say it, you can do bullet points for, even in that. Okay, question 2. Let us rush onwards. Cobalt, transition element, right? So transition elements. These are a bit weird. These are a bit weird and wacky. So complete the electronic structures for a cobalt atom and cobalt in the +3 oxidation state. So this one is obviously, I mean, unless you know a lot of things off the top of your head, is going to require you to have a periodic table, which I don't immediately have to hand. But what shell are transition metals from? What are we dealing with? What shell is the important one when we deal with transition elements? Yes, so D subshells. All right. So that whenever you see the word transition, you are talking about the D subshell. Okay, so there are 3 main types of subshell that you see. There is S, P, and D that you deal with. There is also, you know, there's a whole variety of them beyond that. The only other naturally occurring one is F, but you never deal with that. No one does. They're just kind of weird and out there. S, P, and D, right? Things where, and basically, what type of element something is determined by which shell is its outermost electron in. Okay, so you're only ever interested in the outermost electrons for any element, because those are the ones that do the reacting. So if its outermost electron is in the S shell, those are your group 1 and 2 elements. So those are your alkali metals, alkali earth metals, those ones. Okay. If your P shell, that's the block on the right-hand side of your periodic table. So that, in general, those are your non-metals. And then as you go down further, they kind of start getting a little bit metallic. But again, that's a topic for, well, not even really for A level. So I wouldn't worry too much about that. But yeah, D shell, those are your transition metals. Okay. How many electrons can you have, like maximum, in a set of these shells? So you can see over by here. So you can have up to 2 in a specific shell's s orbitals. Yep. You can have up to 6 in P. How many in D? Yep. 10. So why is that? Let's just briefly talk about that. So as in, what's going on? Why can you have 2 in a set of s orbitals but 6 in a set of p orbitals? So how many electrons can you put in one orbital?
2.
Pardon? In one orbital.
Oh.
Okay, so this is worth talking about, all right? This is very much worth understanding. I know I'm not super talking about the question here, but this is the sort of thing that is very much worth understanding. So shells are what you've been talking about, and you're kind of stuck on shells. That's why you're kind of talking about. So shells are the big numbers at the front, right?
Yeah.
So you have, and shells are your rows of the periodic table, okay? Orbitals are also sometimes known as subshells, right? Subshells is a handy way to remember like what they essentially are, right? So each shell is made up of subshells, which are your orbitals, okay? A single orbital is essentially a box, right? You can think of it as like a box that you can put electrons in.
Yeah.
One orbital can take 2 electrons of opposite spin, right? This is where the whole, wait, I'm trying to draw on the trackpad. That's just a bit weird. So one orbital, and you can have, you've seen this kind of notation before, right? So opposite spins. And that box is one orbital, right? So if one orbital can only take 2 electrons, that goes a long way to explaining why we can put 2 electrons in an S, right? We've got an S orbital, we put 2 electrons in. So how come we can have 6 p electrons in the second shell? Have a guess.
We have 3.
There we go. Excellent. Right? Okay, so it's worth saying, never be afraid to have a guess, right? This is not an exam. Nothing bad is gonna happen if you get it wrong. Okay? So have a guess. It's the best way to learn. Yes. So in the second shell, we have 1 s orbital, but we have 3 p orbitals for a total of 6 p electrons. And then similarly, in the third shell, which is the first one with a d orbital, we have 5 d orbitals for a total of up to 10 d electrons. Okay? Do you know what order things go in with filling up? I'm just going to briefly go through it without kind of trying to ask too many questions. So when you fill up a shell, you start by filling up each box with 1, right? And then you go back and fill up the rest of the boxes with the second one for P. For S, obviously, that doesn't matter because there's only 1, so you put 1 in and then the second one. For D, there is a slightly odd thing that goes on. I'm just going to show it to you. Don't worry too much about it for now. We may come back to it at another time, I don't know. But essentially what happens for D is you put 1 in here, 2 in here, 3 in here, 4 in here. Right, this involves the S for 3 as well, which is kind of weird. All right, okay, no, never mind. We're not going to worry about this for now, actually. This is kind of too off topic, perhaps. I'm just not unfilling my orbitals now. I'd really be one. Okay, so for now, suffice to worry about, we have 3D orbitals. The second point to make is about, hang on. Oh, okay, yes. So this is actually going significantly beyond where we are, but that's fair enough. Yeah, so you're going to have quite a lot of stuff here. Yeah, so 3s2, 3p. Yeah. Okay. So the yeah, all right. So we do actually need to talk about that. So the second point to make is about the 4s orbital, right? So you fill up s before d. There is a very useful picture that you can draw, which I'm going to draw for you now. So if I come over here, if we put 1s, 1, 2, 3, 4, s, s, p, S, P, D, S, P, D, F, and so on and so forth. So if you draw arrows going downwards. I think. Wait, hang on. Am I doing this the wrong way around? I swear I'm not. What do you do? Oh, yes, no, it goes this way. Right, yes. My apologies. So, okay, I've done something very wrong here. I've messed this up somehow, and I'm not quite sure why. Basically, it's worth looking up. You can draw a nice diagram that makes it very easy to remember. Very easy, he says, having completely forgotten how to draw it somehow. I'm still not quite sure how I've done this, but there we go. You can draw a very nice diagram that makes it easy to remember which order you fill up your orbitals in. And I've messed it up somehow. I don't know why, but there we go. Okay, so let's ignore that for now and continue. Sorry about that. Yeah, it's worth looking up though. Just, maybe tomorrow when you're working or something, have a Google of like orbital triangle list or something like that. Basically, you write out a triangle kind of like this, and then you draw diagonal arrows through it, and it like shows you exactly the order that you fill things up in. So yeah, you fill up the 4s before the 3d orbital. That's the general important point that we were trying to come to. But then when you actually oxidize them, you actually empty the 4s first, which is what they were getting at in your cobalt 3+ state. Yeah? So you have 4s2, 3d7, but then once you start ionizing it, you lose the 4s. It's a bit weird, but that's just the way it works. Okay, so I've blathered on about that for far too long. Let's move on. In an aqueous solution of cobalt-2, our cobalt forms complex ions. So what do we mean by a complex ion?
The ion bonded to more ligands, like
Yeah,
to say.
ligands.
Yeah, ligands.
So ligands are essentially things stuck to the outside of an ion, and they sit around and they do some other things. Usually your ligands are water, right? At this level, that's what you usually deal with. So you remember when we were talking about dissolving things, yeah? So the and you remember I was saying that water molecules stick around an ion and form hydrogen bonds, yeah? So essentially, for smaller ions, that just kind of happens in a mess. It's kind of when you get to transition metals, that's exactly what we're talking about when we talk about ligands, except this time you get a much more ordered system, right? So they take a fixed shape as opposed to just kind of a blob, right? So yeah, it's the difference between, a crowd of people. Think about if a celebrity walks into the marketplace, right? And you get loads of people just crowding around them in a complete mess, right? As opposed to, say, the nice pattern of this around the light bulb. Yeah. Obviously, you don't get quite that many ligands, but that's the idea, right? That's the difference. But it's the same kind of, they're all just surrounding your ion. So what does it do that are not shown by an S block element? So the important one for transition metals is multiple oxidation states, right? That is one of the biggest ones that you need to remember. Basically, that's what makes transition metals do all of the important things that they do, is the fact that they, and essentially mostly just they, can have multiple oxidation states. Whereas an S block element will only have one oxidation state. If it's group 1, it'll be +1. If it's group 2, it'll be +2. That's it. That's all there is to it. Whereas the S block ones, the D block ones, they can have lots of different ones. And then, catalytic activity, colored ions. So this is a good example of where these are just bullet points, and they've given you 3 options, and you can have any 2 of those 3. But the oxidation states one is by far the most important, right? The other ones are nice to know. The oxidation states one comes up in a whole variety of places. The oxidation states one is the reason for the other two, in fact. So that's kind of the one that's worth remembering. All right, so cobalt-2 ions show some chemical properties similar to copper-2 plus ions. Unsurprising. Use this information and the data booklet suggest the formula of the cobalt species formed. State the type of reaction. Okay, so how did you guys get on with this question? This is an interesting type of question. This is probably one of the ones that they were more thinking about when they set up these masterclass type things. So what was your thinking when you got to this question? How much of this did you get through before you started having a look at the mark scheme? Would be a good thing for me to ask.
I got the middle one, the CO2 plus O8 because it's kind of a simple one. But like these two, I couldn't get like, why did it get like 3 positive charge and 2 positive charge? Like, it's kind of not sure.
Okay, so did you have a look at the data booklet as it suggested?
Yeah, but like the
So-
I would just back to the table.
So what they are in fact looking at is it's a massive data booklet, so that's kind of a pain. But I don't know. Do you have much on reactions in here? Or was I was going to say otherwise. I'm going to. Yeah. Okay, so it is almost certainly. Yeah. Okay, cool. So this is another thing that's worth talking about. So here we come back to our electrode potentials. Okay. Now we don't need to worry about the electrode potentials and the numbers and all of that complicated stuff, right? What we are interested in here is the fact that on the right, ignoring the numbers, we have a very useful list of all of the different types of reactions that these types of ions can do. Okay? Now you will notice that cobalt is not on here in any place, but copper is, right? They've got a whole list of copper reactions. That's why they've said this, right? So it's learning to read between the lines with the question. That's the most important point here, right? Actually, they aren't looking for any deep chemical understanding here. They're looking for your ability to extrapolate. So they've said they show similar properties to copper ions, but they're cobalt. Use the data booklet. So here we have a list of reactions that copper ions can do. And we've been told that essentially cobalt is going to do the same thing. And so all we're really looking for here is to do the same reactions, pulling them from the data booklet, but putting cobalt in the place of copper. Yeah? So we have, for instance, we have one at the bottom of the list. So we've got 4 copper reactions. One of them is specifically copper with lots of ammonia, right? In the booklet, that's on the right-hand side. Obviously, if we're reacting with ammonia, then it's going to go in the opposite direction. But that's the same idea. So yeah, we're reacting cobalt-2 plus in all of these situations. Yeah. So we can look for the, where the copper 2 plus reactions. And yeah, apart from that, it's all going to be based off comparing it with that one. Yeah. All right. So Yeah, so, oh, actually, tell a lie. So why have they even done that? That's curious. Okay, actually, I've been deeply lying to you. They do actually have cobalt in here. So the copper and excess ammonium is actually just in there. So that one's bizarrely simple. And then cobalt plus the other two is just a matter of finding those two in the list of equations. So they should be in there somewhere. It's a very long list. But they will be in there somewhere, and you can find them and see what they form. But yeah, so, all right, cool. We will continue then. So yeah, that's something that's worth talking about. Obviously, as I say, they were intending for you to try and compare cobalt to copper and look at the copper reactions. However, in fact, they've just got cobalt in there. So that seems a little odd to me, but we'll give them the benefit of the doubt and assume that they meant you to find that. But yeah, that's what, it's always worth trying to figure out what they're doing. There is usually an easy way of doing it and a hard way. And often the easy way is kind of very cryptically hidden in the question. Yeah, testing your detective skills almost more than your chemistry, but there we go. Always a bit fun to play Sherlock Holmes. Transition elements in superconductors, only very bad superconductors, but you know. Oh, okay, they're looking at, kind of, no, it's a bit of a ceramic superconductor, it's not too bad. So, superconductors have no resistance. That's all irrelevant, okay? All this is empirical formula. Yep. This is another exam technique skill, right? Being able to cut things down and go, okay, what's actually relevant? It's 1 mark, it's empirical formula. I'm assuming, are you guys fairly happy with empirical formula? Yeah. You did it at AS, I'm assuming. So what was it in your AS course? Empirical formulas in last year's stuff? Maybe not, never mind. It's a technique that you work through. If you're happy with it, you're happy with it. If you aren't, bring it up in one of these sessions with someone. They'll be more than happy to go through it. I can now if you like, but I'm assuming that we're going to move on. Okay, so table shows our oxidation numbers. Calculate the average oxidation number of copper in Q. So this is just a case of, so this is a slightly odd one. It's a bit out there as far as questions go, but ultimately we're saying, okay, we've got a molecule overall that is not charged, so all of its oxidation numbers have to add up to 0, right? So we can add up the oxidation numbers of all of the other ones, and then we can work out what we're going to need to balance that out to 0. That's going to be made up by 3 copper atoms, and therefore we're going to divide that by 3 to get the average. Now, what I would guess is that we are not going to come out with a whole number. No, we are not. We're going to come out with 7/3 or 2.3. Now, oxidation numbers, can they be fractions?
Yeah.
No.
Oh.
Right? So oxidation numbers cannot be fractions because at its heart, what an oxidation number is the kind of idea of how many electrons has this atom lost or gained. Okay? Now, it hasn't, so in an ionic reaction, they physically lose those electrons and they go to the other atom entirely, right? In compounds that are stuck together, you haven't necessarily lost them. This, if you're interested, you can just once you get used to it, you can tell by the elements. This is actually an ionic compound, right? So these are all ionized. But even in a covalent thing, you can still have oxidation numbers, right? But it's the idea of essentially, in a kind of passing back and forth, how many electrons has it lost or gained from its kind of natural neutral state? All right? Electrons are a physical whole thing, right? You can't chop an electron in half and hand half to someone else and keep your half, right? That doesn't work. Therefore, oxidation numbers can only be a whole number. Which is why when we say our average is 7/3, we're saying we've got +7 from our 3 copper atoms, right? So our average is 7/3, which is 2.3 or whatever. But the second part is saying, okay, we can't actually have 2.3 on each copper atom. So actually what we're going to have is 2, 2, and 3, right? It's going to be as balanced as it can be. So we're going to split 7 up into 3. We've got 2, 2, 2, that makes 6. Stick an extra one on one of them, 2, 2, and 3. Okay? Because that extra electron has to come from one of those atoms. They can't each just kind of hand a third of an atom over and yeah, a third of an electron even, but yeah. Make a bit of sense? Cool. Okay, we shall move on then. I feel bad. I probably should be writing more down, but there hasn't been very much like, I don't know, righty stuff, if that makes any sense. It doesn't make any sense, does it? Never mind. We will move swiftly on. Okay, so we have a grid. It's not really a grid, it's more of a graph, but I don't know what it is. Let's see. So sketch the trend in the melting points of the group 4 elements. The point for germanium has already been shown. Oh wait, that's my my mouse pointer was sitting here, like exactly, and it just looked like it was a point on the graph, and I thought it was, and I was like, but you've shown 2 of them. That was deep. That was deeply confusing to me. All right, so let us see. That was page 3. This is page 4. I don't want page 4. I want page 5. So, melting points of group 4 elements. So, group 4 on the periodic table. Where is it? What side? Don't look at the periodic table. That's cheating. Right-hand block. Yeah. Okay, so it's over there.
Yeah.
So, as we go down the group, is our melting point going to get, is our bonding and our melting point going to get stronger or weaker?
Weaker.
Why?
Because the distance.
Yeah, atoms are getting bigger, so you're further apart, so you're getting weaker bonding. Cool. So, our trend is going to look something vaguely like this type of thing. Obviously, ideally, your line should go through the point. I kind of had a slash at my drawing tablet, so it didn't. But actually, I would have got the mark. The only thing that they are looking for is sketch graph show general decrease. So even that would be good enough, right? All they're looking for is it's going down. I would argue that realistically, this should have been a worded question, right? They were looking for it goes down. For some reason, they decided they needed a graph. Whatever, it works. Suggest an explanation. We just talked about that. Cool. So we have some amphoteric oxides. Right, that's fun. I've actually not heard that word before. What does it mean? It means it can act as both, right? It can be one or the other. It can be an acid or a base. There we go. That was fun. That's just something that we need to know, I suppose. Construct an equation for the reaction of, is that selenium? Yeah, selenium dioxide? I'm pretty sure it is, yeah. It's a bit weird. With sodium hydroxide. So we're constructing a reaction. How are we going to go about doing this?
I would just SnO2 plus NO2 like without like no.
Yeah.
And then, because I thought it's gonna be unproduced water,
Excellent.
and then I just put water, and then like at least just put together.
The rest.
Yeah.
Yeah. Excellent. So that's perfect. So we have just been told that they're acting as an acid/base, right? What is it acting as in this case? It's just worth it. They don't ask, but it's worth asking. Is it acting as an acid or a base in this case? Yeah. Why? How do we know that?
Sodium.
Sodium what? Say it louder. Come on, speak up.
Sodium hydroxide.
Hydroxide. Hydroxide.
Hydroxide.
Not hydroxide. Hydroxide. It's just the one O. Okay. Cool. So yeah, sodium hydroxide is an alkali. It's a very strong alkali. It's a base. Therefore, whatever it's reacting with, it's going to be acting as an acid if it's one of them, right? You're not going to be reacting two bases together very easily. So we know it's acting as an acid. We're reacting an acid and a base. As you so rightly say, we're expecting water. So we put the two of them on one side, we put water on the other, and we get the rest, as it were. Cool. Okay. Interestingly, it does in fact appear that the real reaction is actually something far weirder, where we actually form a hydrated crystal, and we actually react with water. So this is one of those weird questions where actually the right answer is not true. Okay, so your answer is exactly what they are looking for you to do, but they will in fact allow this other thing because that's what would really happen if you reacted those two. And obviously they can't discount the true answer, but what they are looking for is what you've said, right? They're looking for that logic of I'm expecting to form water, and so my product is going to be whatever's left after I've used up water. Okay, cool. And then obviously you do a little bit of balancing because you need two hydrogens to make water and stuff. Quoting information from our data booklet, explain why our reaction between dichromate ions and acidified selenium-2+ is feasible. So this comes back once again to our lovely list. You're going to be very fond of this list by the time you finish this course. We come back once again to our lovely list of ionic half equations. Fun times. What we are going to find is that they react together because they have different, they have sufficiently different potentials. There we go, words, they're useful. So sufficiently different potentials. We're going to flip them around. They're going to react together beautifully. Everything is going to be wonderful. And we're going to be very happy. Yeah, this list is life. So far as I can tell, basically, apart from your kind of, you know, what's it called, the sort of bond things and stuff, you know, IR spectroscopy, all that kind of stuff. Apart from that, whenever they're saying data booklet, we're looking at this list basically, right? Yeah, so there we go. All right, equation for the reaction in C part 1 and give any relevant observations. So again, in C part 1, we would have discovered some nice half equations. Now we're going to stick them together. We're going to give some observations. I'm assuming by the observation that we're either going to produce a gas or lose some color one way or another. They have rather eloquently written, wow, okay, quality stuff. Their mark scheme, the marking point for observations is literally the word green. If you had the word green, you got the mark. That is because, of course, potassium dichromate, green. The color green.
Yeah,
there we go.
That's going to produce gas. Just only say gas.
You wouldn't have got the mark for saying gas because it doesn't produce gas, it produces water. Yeah, so I was saying, so basically when they say observations, there are two possibilities, right? Because when they say the word observations, They are very specifically looking, and this is a thing that trips people up sometimes. They are very specifically looking for what you can see. So actually, there are three possibilities, right? Number one, color change, because you can see that. And that's what we're looking for here, right? It goes green to clear or clear to green. Whichever way around it is, you would discover that from whichever way around your dichromate reaction is, right? In fact, ironically, it doesn't even matter if you get it the right way around. They're just looking for the word green. So good times. But, you know, yeah, preferably get it the right way around. Color change. The second one is effervescence. That's a good word. It means bubbles. I write effervescence because it's a good word. They like it, but it means bubbles, right? If your reaction is in solution and it's producing a gas, you get bubbles. And therefore you write that you are observing effervescence because you will see bubbles, okay? In this case, our reaction doesn't. It produces some ions and water, right? So you're not going to see effervescence because you're not making gas. But in this case, you're seeing a color change. The last one is if you're reacting, and this tends to be quite specific to acids and metals, right? If you've got some kind of solid and you're going to a solution, then you will see the solid disappear. That's the phrasing that they like, right? Because if you're reacting away your solid and it's turning into a solution, then you're going to have a lump of solid that's gradually dissolving away. Those are the three types of things that you can see. So whenever you see observations, you're looking for one of those. So it's, do I have a color change that I know about? If you don't, do I have am I making a gas? And if not, am I using up a solid? Possibly the best way of looking at it is actually a different order, which is, am I making a gas? Am I using up a solid? And if not, then try and figure out, is there a color change that I can figure out? If there are neither of the first two and you don't know, have a guess at a color change. All right? Because at that point, it's going to be a color change, so have a guess. Obviously, that's not super good chemistry, but it's good exam technique, right? Always answer the question. If you have no idea, have a good guess. That is true of the exam, because if you give an answer, you have some small chance of getting the marks. If you write nothing, you are guaranteed to get 0, right? It is also useful for this, right? It is always useful to try and answer a question before you go through the mark scheme and then compare. That is far more useful than just not doing it and then having a look at the mark scheme straight away. So have a guess and improve rather than just doing nothing and waiting for the mark scheme. That's easier. It feels nice because you didn't get it wrong, right? It doesn't matter if you get it wrong. So have a guess. That is the best thing that you can take away from all of this. All right, so we have, right, so we're only on like question. Wow, four is ridiculously long as well. So there are 9 questions on this paper. We have half an hour left out of an hour and a half. So this is why I was saying, let's have a look at some of the harder ones. So we've done some useful stuff going through. However, unless we want to just blaze through and I'm just talking at you, which isn't very helpful, given that you go through the same syllabus repeatedly, right? There isn't necessarily a need to do everything all in one go. So it is far more useful with these for us to do a few questions in depth. And then, the next time we focus on different topics. That's kind of the point of this, right? So you do a couple, you get them down, then the next time you do a couple, and then by the time you've done 4 or 5 sessions or sets, then you've got the whole thing down, right? That is far more useful than just breezing over it repeatedly, because then you've just breezed through it lots and lots of times and you still don't understand anything in great depth, right? So that's what I'm aiming for here. So half an hour left. That's probably time for 2 or 3 questions. So I would like you to, at the very least, pick one each that you would like to go through. that we haven't done yet, obviously.
I'm going to say question 5. There's a bottom. Like,
Okay. Okay, we're going to finish off question 4 while we're at it.
Yeah.
And you keep having a think, and then we'll do question 5 because you've said it. And if you really can't think of anything, we'll just do question 6. But then we're going to miss out 7, 8, and 9, which seems like a shame. So have a think while we're at it. Okay, so briefly going through question 4 then. This one, disproportionation. What is disproportionation? No, that's a different place. There we go. What is disproportionation? Have a guess.
This means like reduce something. Like this.
Yeah, so it doesn't, it's not anything like what the name sounds like. Okay, so this is an important one to know. So disproportionation, fundamentally, disproportionation is redox, right? It is a type of redox reaction. Now, obviously, the name redox comes from reduction and oxidation. Those are the 2 types, right? Disproportionation is kind of the 3rd type. It is, in fact, both types. So disproportionation is where what you start with one species and it is both reduced and oxidized. Okay? In this case, we've started with germanium-2. This is another thing that is worth knowing, okay? Germanium-2, germanium-4, and germanium, okay? Roman numerals, when they are done like that, you see this relatively often, that is an oxidation state, right? So that is literally just telling you in the name the oxidation state of that species.
Yeah.
So that is saying we start with germanium in the +2 oxidation state, and we go to some that's in +4 and some that is in 0 state. It's just plain germanium, right? That if it's just germanium, that's in 0.
Yeah.
Obviously, if we've gone from +2 to +4, that's gone up, so that's oxidation. If we've gone from +2 down to 0, that's down, so that's reduction. So our germanium-2 has been both oxidized and reduced in the same reaction. That's disproportionation, right? So it happens when your one thing goes into 2 separate species generally. And yeah, what I've just explained is the answer to the question. But yeah, so that's an important one to be aware of. Some reactions of cyanogen are similar to those of chlorine. Yeah, blimey. Okay, so this is another example of the kind of thing that we were talking about earlier with copper and cobalt. Yeah. So essentially, what they're asking you to do is essentially ignore the fact that you've got cyanogen at all, right? Deal with chlorine, do everything that you know with chlorine, but instead of writing Cl, write Cn. All right? Seems good. So instead of Cl2, we have Cn2. So this is literally just when you react chlorine with sodium hydroxide, what do you get?
How do you say sodium?
Chloride.
Yeah.
Which is? What's sodium chloride? Come on. You? Sodium chloride. What is it? You see it every day. Come on. You eat far too much of it, I guarantee. We all do. It's salt. Okay? Right. That one is very important to know. Yeah. Sodium hydroxide. So specifically, sodium chloride is table salt. Yeah, that's the salt that we always talk about. In fact, salts are anything that you get from an acid-base reaction. But sodium chloride is common salt. In this case, so you get exactly the same reaction. You get sodium chloride, you get water, and so on and so forth. Yeah, cool. Oh, right, so yes, in this case, we are going to get, in fact, some slightly different stuff. Oh, cold aqueous, right. So this is actually a rather more specific reaction. It's probably, it might be in your data booklet somewhere, otherwise it's one that you need to know about. So this is the one whereby you get sodium chlorate. Oh, wait, I'm drawing on, I keep doing this. So this is the one whereby usually we get sodium chlorate, which is NaClO. Yeah? So usually when you react chlorine or cyanide, dicyanide with this, you get just a whole bunch of sodium chloride, right? In this case, we get some sodium chloride and some sodium chlorate. Okay, cool. Let us move on. Draw a dot and cross diagram for this thing. Show the outer electrons only. That is a bit of a weird one. It's kind of nasty, to be honest. Really? What? Okay, actually, that's completely. Oh, I see. Right, yeah. So it's a bit weird. So yeah, this one is a bit odd. The key thing to realize, I'm not going to draw the whole diagram, obviously, but cyanide ion looks like this. So this is a CN minus ion, right? CN on its own without the minus has a single electron here and not this one. Okay? Actually, I can do better than that. That's CN. As an ion, it's CN minus. It's a triple bond. So if you're drawing a dot and cross diagram, you're putting 3 pairs of electrons in that like overlap between C and N. Okay? Again, it's just kind of something you need to know. It's a bit weird. Room temperature, phosphorus, cage-like structure. Okay. Yeah, it's a tetrahedron. Cool. Yeah. And then this one is just a bit of enthalpy calculations. So this is the whole pathways thing. All right. We can maybe come back to that. I doubt it. Was that okay? Do you want to talk about it, or should we just move on to question 5? We've been on question 4 for a long time at this point. All right, cool. So, are you? Yeah, cool. All right, so question 5. No, that's still question 4. Blimey. Okay, question 4 is absurdly long. That must have been like like a third of the paper was one question. That's ridiculous. I'm gonna have to have words with someone about that. I'm not. No one cares what I say. Never mind. Okay. Student is carrying out some reactions. Hopefully they won't do any damage themselves, but we'll see. Butanal and butanone. Cool. Following results are obtained with reagents L, N, and M. Okay, so what are these? What type of organic? So first of all, we are now on a completely different topic to anything we've dealt with so far. This is organic chemistry. People love it or they hate it. Some people love organic chemistry and hate the physical stuff. Some people love the physical stuff and hate organic chemistry. You're usually one way or the other. There are very few people who like both, even among the people who go and do chemistry at university. So these are the 2 types of molecules that you're introduced to at A2. You did a little bit of organic chemistry at AS and even some at GCSE. These are usually new to you at A2. So what types of molecules are these? Right, one on the left, butanal, and the one on the right, butanone. The ending is what gives you the name. So butanal is an aldehyde. Butanone is a ketone. Aldehydes and ketones. Aldehydes and ketones are all about the carbon-oxygen double bond. All right? That's what it's all about. So an aldehyde has a carbon with a double bond to an oxygen and a hydrogen. A ketone is a carbon with a double bond to an oxygen and another carbon on either side. Essentially, it's, do I have a double bond to an oxygen at the end of a chain, like here, or in the middle of a chain, like here? All right? And they do a set of reactions. I can go through this if you want, but ultimately, this is a set of learnings.
I just want to. I think that's because of my English, but I didn't get the question. A part 2.
A part 2. Give the structure of the organic product formed when M reacts with butanal. Okay.
I mean, I just said I just wrote butanols, the structures.
Okay, so give the structure of the organic product formed when M reacts with butanal. So this is, we're saying we've got M plus butanal, call it B,
Yeah.
goes to something.
Yeah.
And what they want you to do is draw the something.
Okay. Yeah.
Yeah? So M, in this case, is Tollens reagent, or acidified potassium dichromate. What does it do? It ionizes it. It turns it into a carboxylic acid. Okay. So there are a variety of options for M. You can have something called Failing solution. You can have something called Tollens reagent, or you can have acidified potassium dichromate, or you can even have manganate ions. So there's lots of options because it's actually it's a fairly standard reaction to do. It's essentially it's bog standard nucleophilic substitution is essentially what it is. Personally, I would recommend if you need to learning. If you struggle with remembering this one. I would always recommend for these two. So, and you can see again, there's some, so for L, you can have 2,4-dinitrophenylhydronine or whatever it is, lithium aluminium tetrahydride, sodium borotetrahydride, right? Lots of complicated things. Or you can have Brady's reagent. My personal advice would be that if you need to learn answers for things like this, learn the ones where it's just so-and-so's reagent, because that's nice and easy to remember. Okay. It's just someone's reagent, right? So-and-so, it's just a name. That people generally, in my experience, find those easier to remember. You do need to know about all of them in case they ask it the other way around, and they say, they give you lithium aluminium tetrahydride, but that's it's easy enough. It's much easier to recognize something than it is to remember it from nothing, if that makes sense. However, as we were saying, so M, we are reacting with an aldehyde but not a ketone. We are making a carboxylic acid, and so essentially what they are looking for is they just want butanoic acid. Okay. And then actually, more specifically, depending on, well, actually, no. So yeah, that's fine. You can give it as an ionic compound because it's an acid, right? It can form ionic compounds. So you're aware that at least when you're writing them not drawn out, carboxylic acid looks like COOH. They're the COOs. that can become COO minus. In here, they've written it as CO2. I think it's always useful to write them as COO because you're differentiating between the O that's a double bond and the O that's bonding to the hydrogen and being the acid. So you can have COO minus and then like sodium plus or something. Either of those would have been fine, and then you just need the rest of the butane structure. So does that make sense to you now as to why they're doing that? So they're saying, you know, we've said M is doing a reaction with butanol, and they're essentially just asking what is formed, except rather than just asking for its name, they're asking for its structure. Does that make sense?
Yeah, I think so.
You think so?
I think I get it. I get it. Yeah.
Okay, cool. All right, we'll move on then. So, what is observed when N reacts with butanone? So, N reacts with butanone. So, key thing to note here, right? These are a useful thing that they will sometimes ask about. So, L reacts with both. M reacts with only aldehydes. N reacts with only ketones. Yeah. These are often used. So essentially, you can use L and one of M or N as a test to identify aldehydes or ketones, right? L reacts with anything with a carbon-oxygen double bond.
Okay.
M only reacts with aldehydes. N only reacts with ketones. So what you can do is you can react them with L. If it reacts, you know it's one of the two, and then you react it with the other one, and you can tell which one it is. So if you then react it with M and it doesn't react, you know it's a ketone. If it does, you know it's an aldehyde, and so on and so forth, right? So N reacts with ketone but not an aldehyde. It's alkaline iodine, and scrolling down, part 3. I am not on that page. That's page 6. That's page 7. Yeah. So this is one of the fun ones. So yellow precipitate. These are just some of the learn it ones, essentially. Yeah. You make some iodine and stuffs. It's not terribly interesting, I'm afraid. But yeah, yellow precipitate. It's not much to say there. Sorry. There are particularly with these kinds of what do you see when X happens. There's quite a lot of learn it ones. Some of them there's a bit of stuff that you can try and remember to them. There are themes and things that are worth trying to spot, but a lot of it is just you need to know it. Yeah. Okay. The organolithium compound, methyl lithium. So organolithium, these are some weird things, right? It's got a funny name. Essentially, what happens is you have a lithium atom that is pretending to be hydrogen. Okay? So you've got essentially what would be methane, except one of your hydrogens has been replaced with a lithium. Okay? Except because it's not hydrogen, it's lithium, it's a much weaker bond.
Yeah.
So if you have a look, one of you got a data booklet, grab your periodic table. It's worth making a little sense of. So do we have, okay, so we have, unfortunately, we have hydrogen over here in this one. I don't particularly like that. Hydrogen fits in quite nicely here, right? It has one outer electron. Next thing down with one outer electron is lithium. Okay, so they can do similar things, but lithium is much weaker because it's, you know, it's got a shell in between. Yeah. Whereas hydrogen, its only shell is that one outer electron. Lithium is therefore it's much weaker bonding, and so as you can see here, what we've got is we've got that bond breaking down and just leaving the ions. And we've got both of those pair of electrons being left on the carbon species.
Yeah.
And then your lithium has a full outer shell because it's lost its one outer electron. CH3 minus can act as a nucleophile. That means it's attracted to positive charge because it's negative. And then we're going to have some stuff. So suggest a mechanism for the reaction of butanal with CH3 minus ions. Include all necessary curly arrows, lone pairs, blah, blah, blah. So how did you find this? Did you know this reaction reasonably well? How did it go?
I did all like the charges and carry arrows, but the before the step one, and then
Okay, so this one is an interesting one. All right, so this is a nucleophilic reaction at heart, right? So I'm not going to bother drawing most of the molecule because actually the only bit that matters fundamentally is that we have a C double bond O. Oxygen is more electronegative, so that one gets a delta minus, this one gets a delta plus. And then we have CH3 minus, and that has a lone pair. Okay? This is a nucleophile, it's attracted to our delta plus. Our lone pair bonds on here, and our bond up here breaks and goes onto the oxygen. And then you end up with a lone pair on the oxygen, and that picks up a hydrogen. Yeah. And in this case, essentially, this one goes to CH3, and then an O minus with its own lone pair. And then over here, they're saying we add hydrogen. H plus is gonna, this lone pair is gonna bond to the H plus. And that's where your OH comes from. But that's actually not required of you. The only thing you need to do is do this step, right? Now, what's worth noting here is CH3 minus is a bit of a weird one, right? Have you come across that before at all? No, right? What's important here is it doesn't matter. That is the same reason that I haven't drawn most of the molecule, right? And it's the same reason that they're not worried about you doing the hydrogen bit. All they are interested in is the fundamentals of a nucleophilic reaction, which is you have where's my pen? You have a lone pair, which I'm going to circle far too many times and now you can't see it because it's important, right? Nucleophilic reaction, we have a lone pair with a negative charge that is attracted to our delta plus with a double bond. And this happens. And these are our two curly arrows, right? This one goes on here, knocks this one out. You get a lone pair up here, and then that'll stick to something else. Okay? But yeah, so this is an interesting question, but at the same time, it shouldn't be challenging at all in some ways, right? It's there to throw off people who don't know what they're doing unless they've learned like very specific reactions. So, you know, a lot of the time you do this with hydrogen bromide and stuff like that, right? Some people will go, it's not hydrogen bromide, what do I do, right? What they're looking to try and consolidate here is the fact that actually all that matters is your lone pair and your negative charge, your attraction to a positive charge with a lone pair. Okay? And actually that CH3 could be, you know, some weird giant molecule that, you know, has a bunch of things you've never heard of it. You don't care. It's got a negatively charged lone pair. That's all you're interested in. It can be negative or it can be delta negative. That doesn't matter as long as it's attracted to a positive charge. All right? Cool. All right, last bit. And then I think we'll probably call it a day there because we're coming up to 6:30 and it's getting dark outside. A chemist decides to prepare the following organic compound from butanol. Butanal. Don't know why, he just felt like it. Got bored one day. Draw the structure of the organolithium reagent, which could be used to prepare G from butanal. So, butanal, we know what it looks like, right? So I'm going to draw it over here. Butanal, we have there's butanal.
Yeah.
So what we've stuck on is this. You happy with skeletal structures where I'm not bothering writing the CH3s? And so, much the same way, this bond here needs to have come from a lithium.
Yeah.
Because then what we would end up with, once you lose the lithium, is you would get this with a lone pair and a minus, and your, CH3, CH3. And, this is a carbon with this is a CH2 over here. They've just not drawn that because it's skeletal. Yeah? CH2, CH3, CH3. Your CH2 minus with a lone pair. That's going to be attracted to our delta plus over here. And you're going to get, it's not a very curly arrow, but that'll do. This is delta minus, and you've got exactly the same reaction, right? So essentially what you want to look for is, where is my oxygen? Here's my oxygen. So this is the carbon that had to be my aldehyde to start with. This was my butanal part of the chain. And therefore, this is what I needed to add. So that's what you're doing, right? You're trying to split it into, what did I start with? What used to be my butanal? And you do that by finding, essentially all you're doing here is, and this is easier when you've got the paper in front of you, right? Because these would be on consecutive pages. Here is your butanal. And so it's much easier to spot if you hold them side by side and you just go, oh, look, that bit by there looks a lot like butanal, except with the OH rather than the double bond O. We've just done a question on that. We know where that OH is coming from. And therefore, I needed to stick this bit on. So I just put a lithium where the bond is. Okay?
Yeah.
Excellent. So yeah, draw the structure. It's just lithium instead of this bond here. This is the extra bond that we've added. And we've got CH2, CH3, CH3. Okay?
Yeah.
Excellent. Right. Okay, I think that will probably do us. I'm assuming that, we have 1 minute left in theory, unless you guys want to sit here for even longer. But I'm assuming that you would quite like a break now after an hour and a half of solid going chemistry. So, right, let me find Google Hangouts. Let's stop. Goodbye stream.